of Engineering at the KD, Ranjit.
Thank you very much, Priyanta. Good morning to everybody. Ladies and gentlemen, we all have experienced power failures at crucial moments. We think they are too frequent and sometimes too long. What is the reason for this? These are issues in planning, maintenance, and operation. When it comes to generation and transmission planning, our country practices internationally accepted standards. Sometimes there are delays in implementation, but the planning process cannot be questioned too much. But when it comes to distribution, the situation is different. The practices differ from place to place, differ from person to person, and some of these practices are not good enough. Thus, the distribution network is the weakest link in the supply chain of electricity. In this presentation, I am addressing a specific problem related to distribution reliability. That is, a 33 feeder. When there is a failure occurs somewhere, we have to disconnect a section of consumers. Now, if the failure occurs at the very beginning of the line, we have no choice other than to disconnect everybody, because in Sri Lanka, we have radial type networks. There is no way of supplying from the other end. Now, this example is an example from North Central Province, Anuradhapura Horopatana feeder, which is 258 kilometers long, supplying 10,000 odd customers. If a failure occurs at the beginning, you have to disconnect everybody. There is no other choice. But if the failure occurs somewhere at the end, then also you have to, then it would be absurd to disconnect at the very beginning and keep 10,000 customers out of supply. That is the specific problem we are looking at. Then what is the solution? We can put sufficient number of breakers along the line at strategic positions. Then if a failure occurs at the end, the disconnection occurs at the last most point, and then only part of the customers are disconnected. Now, how are we doing that today in Sri Lanka? Based on past experience and intuition. No systematic method is being used. Sometimes we don't put any. Now here in this, we are developing a methodology to model the distribution line, and then based on that, decide on the number of breakers and the positions they are to be best placed. The first thing is to model the failures in the transmission distribution line. Failure rates depend on the landscape the line is going through. If it is going through thick jungle, the causes are different. It can be tall trees, animals, big animals, and such lines are not observed continuously by the utility going public. In coconut plantations, the situation is different. Paddy fields, more lightning effects, and urban areas, there are other issues. And like that, from area to area, the causes for failure and failure rates are different. But we don't have data for that. We have feeder-specific data. We know how many failures occur in feeder 1, how many failures occur in feeder 2. But we don't know how these failures are to be distributed depending on the landscape. Now, in this method, we are finding zone-specific failure data through the feeder-specific failure data. For that, we write two simple mathematical equations where lambda j represents the feeder-specific failure data, lambda I represents the zone-specific failure data. For a given feeder, lambda j is available, the lengths are available, lengths are Lj and Lji. Lj is the length of the whole line, Lji is the fraction of that line going through a particular landscape, say paddy fields or so on. Now, we have used data available in 16 different feeders to find out zone specific data, but we have identified only 6 different zones. Then there is some redundancy, and we used least square feet to come to a solution, and the solution was the thick jungle has the highest failure rate expressed in failures per kilometer per year. Semi-urban areas where you have a lot of vegetation and human activity comes next. Paddy fields are relatively high. There the reasons are completely different. The lines going through paddy fields are exposed to lightning. So lightning contributes to the failures in paddy fields. General vegetation comes close to that. Urban areas are the best, but coconut plantations are the best actually, because coconut trees do not branch out, and the people who maintain the coconut plantations make sure that all trees are removed in time, because they have financial value as well. And now with this data, we are in a position to map failures along a line at any position to the other side. And we use that information to find out the best number and best positioning of the switches. And we identify the position for the switches is just prior to the transformer or a spur line. Spur line is a branching line, because that gives us additional advantages. We can maintain the transformer or the spur line issues when the breaker is positioned like that. And I name them candidate locations. And for a line like the example I have shown, there are many and the annual cost of the switch. Then the cost of the interruptions. The cost of the interruptions are faced by the customers. When you have a power failure, there is the cost of unserved energy, and that one is modeled using average interruption duration and the number of customers affected. That data is also available, and cost of unserved energy and the average consumption. I have to mention here the cost of unserved energy figures we have taken from CEB, and this CEB data is based on a research done by Professor Vijaytunga, who is chairing this session today. Now, using this, for each constellation, we can calculate the customer side cost and the utility side cost. When you have more breakers, the customer cost is going down. When you have more breakers, the utility cost is going up. And the sum has a clear-cut minimum. That is the optimum point. And by using the model developed and the cost function, you can find the optimum, the best position. And that is the algorithm we have developed. And of course, I think that ends my conclusion. Conclusion, we have developed a mathematical model for failure rates at different locations along the line, and also another algorithm to find the most economical number of switches and their optimal location. This will be presented to CEB. I hope they will make use of this, because software can be easily made to use this thing, and computers are readily available everywhere. Data is available, so it is a very small step to implement this. And through that, we hope that our reliability levels will improve from the distribution point of view. Thank you very much.